This is our second session of our introduction to multivariable calculus. Last time we talked, we went over a whole bunch of information about vectors. Most importantly, we talked about something called the dot product and the cross product, which were kind of new pieces of information. Up until that, the only thing that we knew how to do with vectors with multiplication was to multiply them by scalars, so multiply them by numbers. With the dot product and the cross product, now we can multiply vectors by other vectors. And the dot product was the one that gave us a number answer, and the cross product gives us another vector that is orthogonal or perpendicular, but orthogonal to the first two. So the dot product gives us a number answer, the cross product gives us a vector answer that is orthogonal using that right-hand rule that we talked about last time. So now that we're familiar with vectors and a bunch of things that we can do with them, we can start talking about vector-valued functions, which is what we're talking about in this session. The nice thing for us is we've seen parametric functions before, which is where you define some function in terms of a new parameter. Usually we call it t or theta, and that's exactly what we do with vector valued functions. So I know that r represents a vector because I have it written here in bold. R is bold, so it's a vector. And then r has three components, so this is a three-dimensional vector. R has a first component of x, a second component y, and a third component z. Now I'm defining those components as these three parametric functions. So our first component, x, in terms of t, is just defined as just t. Y, our second component, in terms of t, is t squared. And z, our third component, is t cubed. And this is just a basic example of a vector-valued function where I really have three parametric functions, or I could have two if it was a two-dimensional vector, but three parametric functions sort of set up in this vector that all make up one vector-valued function. So one of the most basic things that we want to do with vector-valued functions is visualize them on a graph. Before we do that, I just want to talk about the orientation of this three-dimensional graph really quick. Last time, in last time's session, we talked about something called the right-hand rule, which we talked about in the context of cross products. But the right-hand rule says basically you point on your right hand, your pointer finger goes in the direction of your first vector. Your middle finger, which has to sort of be like inside, kind of on the inside of your palm, like inside your hand, points toward the direction of the second vector. And then your thumb sort of points, whatever direction your thumb points in is the direction of that orthogonal third vector. And that comes in with our three-dimensional graph here as well. So if I'm taking my right hand and I put my pointer finger in the direction of the x vector, or the x axis, so my pointer finger is going to go this direction in the direction of the x. Now I have to turn my hand a little bit to make my middle finger point up in the direction of the y axis here. So the way that my hand is oriented right now to make this right-hand rule work is that my palm is facing sort of upward, like my palm is sort of facing the y direction right now. And then when I have my hand like that, my thumb is sort of facing back toward me, which tells us that the positive z direction is back this way. Now, if you had had your hand oriented in such a way that your thumb was sort of pointing toward your piece of paper, then it would tell you that the positive z direction is this way, but it's not. So the reason I'm pointing this out is because sometimes on a three-dimensional graph, some people will change the orientation of x and y and z. So on this particular graph, we have x heading to the right, y going up, and then z is pointing toward us. I think sometimes a more standard notation is to have y facing, sort of coming toward you where we have our z axis right now, and then z going a different direction. The right-hand rule is important because when people change the orientation of this plane, you need to know which direction is the positive direction. Now, when we were just dealing with two-dimensional graphs, just an x and a y like this, we always knew that this is the positive direction for x and then up is the positive direction for y. When we start throwing in a third direction with z, sometimes when people switch these letters around, it's not always clear which is the positive direction. In fact, sometimes the way that we have the space oriented, your positive direction on this third axis will be sort of into the piece of paper, like going back this way. So using that right-hand rule before you do any graphing helps you to know which direction is positive. So we've just verified that this way to the right is positive on the x-axis, up is positive on the y-axis, which is nice, it's what we would expect, and sort of out this way is positive on the z-axis. And that is good to verify before we start graphing anything, which is what we're about to do. So our first example says, describe the graph of the vector valued function given by, and this is bold so I can tell it's a vector, cosine of t, sine of t, and then just t. So something that I want to point out here before we start graphing anything is that if this were a two-dimensional vector, just cosine and then sine, we would know exactly what it looked like, because in 2 dimensions, just cosine and sine like that gives us a circle. Specifically, it gives us a circle of radius 1 because there's these invisible 1s out in front of the sine and the cosine. We're still going to have something like that here in 3 dimensions, but we're obviously going to have to change something a little bit because of that t value. So let's think about, as I increase t, if we were just thinking about 2 dimensions, if I increase t, like when t is at 0, our cosine value starts at 1, so I'd be over here at positive 1 on the x-axis and 0 on the y-axis because sine of 0 is 0. And then as I increase t over to pi and then all the way around to pi over 2, it makes this, this whole circle. Now, what's going to happen here when I throw in this third component is that now when I would be up here at this pi over 2 value, I'm still going to be at the x value of 0, I'm still going to be at a y value of 1, but I'm also going to be sort of coming out of the paper at a t value of pi over 2. So it's like I need to take this dot and just like pull it out of the paper just a little bit out toward you, a pi over 2 length. And then when I get over here to a t value of pi, I'm still going to, oops, this should be a vector. I'm still going to have a value of -1 and then 0, but now I'm going to be up a little bit more out of the paper at a value of pi steps above the piece of paper. So you can probably see what's going on here. I'm sort of like walking, as I walk around the circle, I'm also walking like up the stairs. It's like a spiral staircase going up. So this is going to create a helix. And our helix, this is going to be really hard for me to draw. Our helix is going to start at a value of t equals 0 right here. And we're going to be coming out toward the z-axis, but still just spiraling around. So I'm not sure what the best way is to draw this, but it's going to go something like this, all the way around that z-axis, and this will just go for infinity. And also, I have it stopped right here, and I said it started right there, but actually, you could just as easily do negative t values back here, and your spiral staircase would sort of extend back into the page for negative t values. Obviously, the first 2 components of our vector are periodic, so we're still just going to have this circle. It's just going to sort of like spiral all the way around the z-axis, sort of coming out of the paper that way. So there's our vector valued function, and what I didn't mention and what I should have mentioned here is that when I'm saying vector valued, there's actually infinitely many vectors that are defining all of these points. Every single vector starts at the origin, but I could define all these vectors. And as we're tracing out the vectors, we're tracing out this, in this case, helix. So that's sort of like our basic introduction to vector-valued functions. Now, at this point, you can do exercises. If you want to stop and do some of the problems, you can do exercises 1, 2, and 3, because 1, 2, and 3 are just asking you to basically do exactly what we just did. So describe the graph of, in this case, just a 2-component vector-valued function. The second one, I think, is a 3-component vector-valued function. You'll notice it's sort of similar to the one that we just did, although now the coefficients in front of sine and cosine are different, and we have a negative t. So think about what that does to the graph that we just thought about. And then kind of an interesting problem, number 3. So show that the graph of this vector, remember, using the I, J, and K notation is exactly the same as using these curly or pointy brackets. So I could just as well write this as sine of t, 2 cosine of t, and then square root of 3, sine of t in that third component. So I just wrote it with I, J, K instead, but this is just a 3-component vector. Your job on this third problem is to show that this is a circle in 3 space. It's a 3, so it is a circle, it's not a sphere, but it's a circle in 3 space. And what I mean by that is it's not completely lying in the XY plane, it's a little bit tilted, so we need 3 dimensions to be able to draw it, but it is still a circle. The hint is to do this by showing that the curve, this vector-valued curve, lies on both a sphere and in one single plane. So once you do that, then you'll find its center and its radius. So you can stop here if you want and do those 3 problems before you continue, or you could go on to the next video and see the second part of the lesson.